Hello and welcome to my channel. Today we're gonna talk about the expectation values for operators. So let's get started. So first, if you consider classically, you have a variable, for example, you have a variable q. If you have a variable q, you can take the value of it to be q1 to set qn, right? And the probability would be the coefficient. So it will range from p1 to pn as well. And the expectation value now is the sum from 1 to n of the probability and the value pi. And with this, we can move to the quantum world. So in a quantum system, right, when you have a psi star of x and t times the psi of x and t in in what do you call it? In an interval dx, the probability finding it in x to x plus dx would be this star t, right? And no, that is, or dx, because now we assume that our wave function is a complex function. And when you have this, we can define an expectation value for an operator, that is the position operator. We write the expectation value of x operator is equal to, well, there are multiple ways to denote this, but for now I'm not going to use the bracket notation because it can be quite annoying to see for like those first timers. So I'll just write it in the textbook way, which is this, the star times this. Yep. And we have the same for momentum. We can write first, if you have a function for momentum, for example, like phi of p, that in dp, this would be the probability to get the particle that has p in the interval p to p plus dp. And you can do the same for it here. But of course, you can also write it in the x space, which is the more popular way to write it. So this guy here in p would be this dp. And in x, this would be a p operator, as we said before, is equal to this thing right here, h bar over I, the partial derivative. There we go. This is the expectation value of p operator in p space and x space, respectively. So from this, you can get that if you have an arbitrary operator q hat. So for operator q hat, the expectation value of it in psi would be psi star, the operator in the middle, and psi dx. So suppose your psi is x dependent. And next, we're going to talk about the expectation value for Hermitian operators. And quick reminder here, a Hermitian operator has a property that is right here. I'll write it. No, not H. Q is equal to 0. And if satisfied, and you would get that Q is Hermitian. So with a Hermitian operator, it's basically kind of the same for this, but it will have some special cases. For example, the first one would be that the expectation value of the Hermitian operator in psi is real, meaning that if you take the complex conjugate of it, it would equal to itself. So this would equal to this. That is our claim number 1. The second one is that the eigenvalues for our Q hat are real. Just like first one, the second one, so eigenvalues of Q hat are real. Remember that. And the third one is that when you have a normalized wave function, the expectation value of your Hermitian operator would equal to the eigenvalue itself. So let's, for example, take a collection of eigenfunctions and eigenstates of Q. So it would be easier to see the number, the third one. So the third one for normalize psi just right now. Q hat equal to eigenvalue. So let's take a set of eigenfunctions and eigenvalue right here. So for example, you have your Q acting on psi 1, Q on psi 2, Q on psi 3, and so on. Your wave function is the superposition of all of these eigenfunctions. So this would give you that this is equal to, I'll write Q1 psi 1, Q2 psi 2, and Q3 psi 3. And remember here, Q are real, and when you have this, these are interchangeable. So basically, that's it for number 3. And next one, maybe not the final one. No, it is the final one. So when you have this, these eigenfunctions can be organized so it would satisfy the orthonormality. So which means that I'll find a place. So when you have these eigenfunctions, right? Alright, eigenfunctions can't be organized to satisfy the orthonormality, which means that the integral of star I and psi j would be equal to delta ij, the Kronecker delta. So this would ensure that if I and j are different, the solution would be 0, and if they are the same, the solution would be 1. That is what the Kronecker delta does. So this is the orthonormality of the thing. And focus here that it is said that it can be organized to satisfy this. Doesn't mean that if you have a set, it is already gonna satisfy this automatically. Yeah. So it can be organized to satisfy this. Alright, next is the time dependence of these expectation values. So let's write it here. So to test the time dependence of these expectation values, you would, well, obviously put a derivative relative to time in front of the expectation value. You expand this is psi q psi dx. And once you do a little bit of, well, math and stuff, you can kind of put it back to the Schrodinger equation, and you would get something as IH bar ddt of your expectation value. This will equal to the expectation value of a commutation between the operator you want to test the time dependence and the Hamiltonian itself. There we go. And this is called the Eigenfest theorem. You can prove it, not quite long, but yeah. The Eigenfest theorem basically is a mean for you to test the time dependence of your expectation value. So we already know some operators that commute with the Hamiltonian. So first one is obviously the Hamiltonian itself. The total spin, you will learn about that later on. Well, the total spin, but without the spin orbit coupling, would be able to commute with the Hamiltonian. And I think does P commute with Hamiltonian? Yes, it does. P also commute with the Hamiltonian. Those are some prime example for this. There are a lot more, obviously, like the total angular momentum, I believe, commute with the Hamiltonian too. And yeah, and I think that's the end for today's lesson. Goodbye.